All right. Here's a little bit more complex one that you guys can do. Um, so we're now back to water. Okay. And what's the energy change for 25 grams of steam? Okay. So now we have steam. So we're starting at a high temperature that's cooled from 150 degrees Celsius to ice at negative 14. Okay. So if you look at it, we're going from above the boiling point of water all the way down to the liquid stage, to the solid stage, and cooling it past that. All right. So this is an energy change. Plus, it's opposite because we're cooling it now instead of warming it up. Okay. So instead of gaining energy the whole time, we should be losing energy the whole time as you do this. All right. I'm not going to give you any more than that. Draw it up. If you take a look, there's lots of steps to this one. It should take you a little while to work your way through it. Once you're done, we'll give you the answers here. Okay, so hold on. All right. Hopefully, if you haven't paused the video, pause it here. I'm sorry, I should have said that. Pause the video and then work it out and then come back to me. All right, here we go. All right, so once again, we need our thermodynamic table to solve this thing, to have this up and running. Hopefully, you grabbed that from a previous slide as you did this. Sorry about that. And once we have that done, we had 5 different steps to this thing, okay? So looking through this process, I'm going to draw it up as we kind of work this thing out. We started high. We were way up here, and we were at 150 degrees Celsius. So I had to cool down first, and then I had to condense, and then I had to cool down some more, and then I had to freeze, and then I had to cool down some more. Okay, so I'm seeing 1, 2, 3, 4, 5 legs to this problem. All right, and in this one, I'm going to use MCAT, and my C value. If we take a look at that, oops, I'm going to back up one. My C value for steam, if I look that up, is 1.9 joules per gram degrees Celsius. I'm going to condense, so now I'm going to look at the heat of vaporization for water. It's 40.7, but my delta H of vaporization is going to be a negative 40.7 kilojoules per mole. It's negative because I'm condensing, not vaporizing. In this leg, my C value is going to be waters, so 4.18, which we're comfortable with, hopefully by this point. Joules per gram degree Celsius. In this leg, I am now freezing, so I'm going to use the heat of fusion for water, but the negative version of that, which is 6.01 kilojoules per mole. And then finally, I need another C value here, which is ice's C value, which is 2.09. And that again is joules per gram degrees Celsius. Okay. Now, for each one of these legs, I would expect a temperature change for each one of these to be negative because I am cooling it down. So remember, as you go temperature final minus temperature initial, my final should be smaller than my initial. So we should get a negative value for each one of these legs. So I should get a negative answer here, a negative answer here, a negative answer here, a negative answer here, and a negative answer here. That's my expectation, okay? So before I even did any equations, mentally I had to work my brain through all this stuff. What are my C values? What are my H values? What is everything I have? And then now I can plug it into my equations, okay? So here we go. All right, so we drew it all up, okay? And Q1, 25 grams. I used my C, negative temperature, went from joules to kilojoules. Q2, more heat of vaporization, negative. I got my moles, got my answer. Q3, my grams, water C value, change in temperature is this. Q4, heat of fusion, negative. My moles, got my answer. Q5, grams, specific heat capacity for ice, change in temperature, got my answer. Add all these things up, okay? Rounding this thing back to the tenths place because this guy right here has the least precision, and this one here, and this one here. And we get negative 78.5 kilojoules of energy here, all right? Often I have students ask me the question, Wouldn't it be easier if I just said, what is the temperature or what is the Q change from here to here? So can I just do a single temperature change from here to here and do one Q for the whole range and then just add in the flat lines? So why can't I just go 1, 2, why can't I put parts 1, 3, and 5 together? Okay. Pretty common question actually is, I mean, they're all temperature changes. Why can't I just put them all together? Why do I need to have 3 separate calculations for this? Well, the answer is because the slope of each of these lines is different, because the C value, the 1.9, 4.18, and 2.09 is different, okay? You can't use them all the same because which of these 3 values would you use to make that solution, okay? So if you're thinking about that, it's a pretty common question I get on this problem is, can't I just do it all in one big package? The answer is no. Unfortunately, you can't do that. All right? All right, so that's kind of a big one. Can't get any bigger than this. Okay, I took you through all 5 steps. I made it negative. So if you can do this, you're golden. You know how to do this.